Hi everyone, welcome back to Dave's Math channel. This video is another solution to a recent daily math problem I posted in the Facebook group Classical Mathematics. Specifically, the problems to characterize primes of the form x squared plus 5y squared and 2x squared plus 2xy plus 3y squared. These are two binary quadratic forms. Anyway, let's begin. So here's the specific problem statement. There's four parts. And parts A and B are pretty straightforward, just doing a numerical brute force search. C and D are a lot trickier. They require analysis. So anyway, so part A, I'm asking for which primes up to 100 are of the form x squared plus 5y squared, where x and y are integers. And then for part B, I asked a similar question for primes of the form 2x squared plus 2xy plus 3y squared, primes up to 100, where once again x and y are integers. And then for part C, I'm asking you to prove that for all primes of the form x squared plus 5y squared, doesn't matter how big they are, the only primes of this form are either p equals 5. That one's pretty easy to see. If you just let x equals 0 and y equals 1, you get p equals 5. It's a special case. And all the other solutions are either congruent to 1 or 9 modulo 20. In other words, if we divide by 20, if we divide the prime by 20 and compute the remainder, it's always equal to 1 or 9 modulo 20. Uh, and then for part D, I'm asking a similar question. I want you to prove that for primes of the form 2x squared plus 2xy plus 3y squared, and then there's a special case where p equals 2. If you set y equals 0 and x equals 1, I think you can see p equals 2 is the solution. But all the other primes have to be congruent to 3 or 7 modulo 20 for that case. Anyway, so how do we do this? Well, let's do A and B first. So A and B are pretty easy. You just do I just did it with a numerical brute force search. So you can look at the code I wrote in Mathematica to solve each of these parts, and they're both very similar. All I'm doing is I have these nested for loops. So I'm first I have this parameter p max, which I'm setting equal to 100. It just goes through all the primes up to 100. Actually, it's going through all the integers, positive integers up to 100 first, and then it's just trying different values of x and y. Actually, I think the way I did this, I'm looping over x and y actually, and you can actually find bounds on x and y that require that that they require the result to be less than or equal to p max. In this case, 100. I did that, and when I ran the code on the left, this is for primes of the form x squared plus 5y squared. These are the results I got. These are the only primes of this required form, x squared plus 5y squared. I even printed values of x and y to make it work. So I think you can see what the solutions are. 5, like I said, that's kind of a trivial solution where x equals 0 and y equals 1. Next one's 29, which you get when x is 1. Is that right? X is 2 and x is 3 and y is 2. And then you get 41 when x is 5 and y is 1. 61 when x is 4 and y is 3. And 89 when x is 3 and y is 4. So those are the only solutions you get of the form x squared plus 5y squared. And then I wrote a similar code for doing the other form, 2x squared plus 2xy plus 3y squared. It turns out in this case you actually get a kind of a twofold ambiguity. There's always two essentially different solutions in x and y that give you the same prime, it turns out. In the first case where you have x squared plus 5y squared, these are essentially unique. They're not quite unique because you can negate x or y, replacing x by its negative or y by its negative. I think you can see the squares stay the same. And since the result only depends on the squares, x squared plus 5y squared, you can see that, there's actually 4 solutions that give you a given prime value. But for part B, there's actually 8, I think, and I think there's still 4, but you get a twofold ambiguity, and I commented out a couple lines here that give you the other values of x and y. But anyway, the important thing here is the primes you get, and it turns out you get more solutions. In this case, you get a total of 8, and those primes for this case are 2, 3, 7, 23, 43, looks like 67 and 83. So those are the only solutions you get for part B. I mean, pretty straightforward numerical search. You can see that these are the only solutions up to 100. So that was the easy part of the problem, believe it or not. And now for the hard part, we actually can't, computer's not going to really help us with this part. We have to do analysis. So to prove, usually when you prove things in math, you have to actually do some analysis. You can't prove anything with a computer, really. But anyway, so the trick here, you remember what we want to prove? We want to prove that every prime of the form x squared plus 5y squared is either equal to 5 or congruent to 1 or 9 modulo 20. Well, we can get that by doing modular arithmetic. We just look at a finite number of cases of x, in this case x mod 10 and y mod 2. It turns out that does it. So I go through all possibilities for x mod 10 and y mod 2. And we only really care about their squares. So I put plus or minus here because when you square it, the plus or minus sign cancels. We're just left with the thing we get for the plus sign. So there's really only sort of 6 possibilities for x0 plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, or plus or minus 5 modulo 10. And for each of those cases, I list the values of x squared, which are 0, 1, 4, 9, 16, and 5 mod 20. And they're repeated twice because there's 2 possibilities of y mod 2. Y could be either be even or odd. If y is even, then y mod 2 is 0. And then the other possibility is y is odd, where y mod 2 is 1. And then if you square it, what's interesting is that there's only 2 possibilities modulo 4 for y squared. It's either 0 or 1 mod 4. If y is even, y squared is 0 mod 4, and if y is odd, y squared is 1 mod 4. It can never be 2 or 3 mod 4. So now we have to kind of combine these results. Actually, we have one more step. We have y squared mod 4. We can just multiply that column by 5. That'll give you 5y squared mod 20. And if y squared is 0 mod 4, then 5y squared mod 20 is also 0. And if y squared is 1 mod 4, then 5y squared mod 20 is 5. And now we have all the possibilities for x squared mod 20 in the second column and 5y squared mod 20 in the fifth column. And now we can just add them. So in the last column, we get x squared plus 5y squared mod 20. And this last column lists all the possibilities. But notice that some of these numbers I put in red. The ones in red can't be prime because there's only one even prime, namely 2. And all the other even numbers in this last column are not equal to 2. They're 0, 4, 6, 10, 14, or 16 modulo 20. So none of those will work. None of those can be prime. And then the only ones that are left are the ones we want, 5, 1, 5, and 9. And we know that 5 is the only prime that's congruent to 5 mod 20. So p equals 5 is kind of a special case. And every other prime has to be either congruent to 1 or mod 9 mod 20. So that completes the proof of part C. Modular arithmetic, that's the key here. And we can use it again to solve part D. And we can actually use a little trick for part D. We can rewrite this quadratic polynomial, 2x squared plus 2xy plus 3y squared. We just do a little algebraic manipulation on it. It's equal to 1/2 times 4x squared plus 4xy plus 6y squared, but then we can complete the square of that thing inside. You get just 1/2 2x plus y quantity squared plus 5y squared. And if we call 2x plus y w, then it's equal to 1/2 the quantity w squared plus 5y squared, where w now has to be odd because it was equal to 2x plus y. So we know that it has this form. It's 1/2 times w squared plus 5y squared, where y is an arbitrary integer and w is an arbitrary odd integer. Well, now we can kind of go back to the last table, but we're not considering every possibility here. Actually, another thing you should notice is that if w is odd, notice that 5y squared, I think I made a mistake here, yeah. If y was even, then w would be, this counting, oh yeah, okay, it has to be divisible by 2. W squared plus 5y squared is divisible by 2 because we're dividing it by 2 to get 2x squared plus 2xy plus 3y squared, which has to be an integer. And the only way that that can be true is if y is also odd. Because in that case, is that right? Remember w was odd? Yeah, so if w is odd, if y was even, then 5y squared would be even, and the thing in parentheses would be odd. And we can't divide an odd number by 2 and get an integer, so that means that w and y both have to be odd. And now there's not too many possibilities to look at. Let's see. I don't know if I really use the table here. Yeah. So w squared plus 5y squared has to be even, and the only possibilities on this table are 0, 4, 6, 10, 14, and 16. Actually, I think we could simplify this a little bit more because we know that y has to be odd. That means that we're looking at the bottom half of the table. So the only even values of y we need to consider are 6, 10, and 14, which correspond to, and that's modulo 20, yeah. So that means it has to be either 3, 5, or 7 mod 10, or the special case p equals 2. P equals 2 is pretty easy to see, because if you just let y be 0, you see you'll get p equals 2. But otherwise, it has to be 3, 5, or 7 mod 10. How do we know it's 3, 5, or 7 mod 20? Well, there's another thing you can notice here. What's the value of x squared plus 5y squared mod 4? Or w squared plus 5y squared mod 4. 5, remember, y was odd. That means that 5y squared is congruent to 5 mod 4, or 1 mod 4. Yeah, am I doing this right? I think we want a mod 8, actually. Yeah, so 5, yeah, actually 6 mod 8. Because 5y squared is congruent to 5 mod 8. Well, it turns out that the square of any odd number is always congruent to 1 modulo 8. That means that 5y squared has to be congruent to 5 mod 8. And then w is odd, so its square is congruent to 1 mod 8. That means that w squared plus 5y squared is congruent to 6 mod 8. That means when you divide it by 2, the result is congruent to 3 mod 4. And the only possibilities that are congruent to 3 mod 4 are 3 or 7 mod 20, plus the special case p equals 2. You can't have 13 or 17 because those are congruent to 1 mod 4. So that completes the proof. Anyway, so yeah, like I said, parts C and D are a little bit complicated. But this is an important problem. There's a book. There's a pretty advanced book in algebraic number theory by David Cox. I have it here. It's called Primes of the Form x squared plus ny squared. In this case, we're looking at x squared plus 5y squared. And that book, they look at a lot of different values of n and show you exactly what primes are of that form. And it turns out, this is not just if for x squared plus 5y squared, it's if and only if. I think it turns out that every prime that's congruent to 1 or 9 mod 20 is of the form x squared plus 5y squared. We didn't prove the only if part. And then I think it also turns out that every prime of the form 2x squared plus 2xy plus 3y squared, that's prime if and only if, in this case, p equals 2 or p is kinder to 3 or 7 on 20. Those are a lot harder to prove. So there's a lot of advanced math connected with this problem. But anyway, this completes the problem. So anyway, thank you for watching. Long live math, and I'll see you guys next time. Bye.